Alright, welcome to Temple of Pwn Part 5. Today I'll be talking more about some heap stuff and fast bins, small bins, unsorted bins, and then the House of Force attack. So, this slide you probably recognize since I did it earlier in our use after free meeting. The heap is where data is allocated with mallocs or alex of any type. Data is usually allocated in chunks. For 64-bit, this will be in 16-byte chunks, and 32-bit will be 8-byte chunks. For the most part, we'll usually only look at 64-bit binaries for this, as that's kind of the common or mainstay nowadays. The chunks also include some heap metadata and then data between the chunks to keep track of the chunk sizes and whether they're in use, and some other stuff that I'll talk about in a little bit. So here we'll talk about the arena. Here's a little link that, honestly, if you just search malloc internals, it's probably like the first thing that always shows up, and it has a really good overview of kind of how everything kind of works together and what everything is. So the arena overall is kind of just a structure containing pointers to one or more heaps, and all. So the arena contains pointers to one or more heaps and all pointers for free chunks within those heaps. It's like when I say more than one heaps, I mean if you're allocating a chunk that's probably too large, or you over allocate a certain heap, you might mmap another chunk, and that's considered, I guess, a second heap, so the arena will kind of keep track of that for you. So what the arena, like overall, this structure contains is the fast bin list, the top chunk pointer, which will be referred to as the wilderness most of the time, pointers within unsorted bins, within the unsorted bin, the unsorted bin pointer, the fast bin pointer, the small bin list, and then the large bin list. So that's kind of a large area of stuff, but that's kind of just everything that it includes. See, here's kind of what it actually looks like. So if on the left is in-use heap bins from Jeff, and you can see the T-cache. We don't really care about that, but we can see that we actually have the fast bins and an unsorted bin. And then if you actually look, the fast bins for the arena is at this address. So if we were to dump this address, the first two, I'm pretty sure that they regulate whether the first two 8 bytes, so 16 bytes, regulate whether the chunk is in use, as in the fast bin, and then these chunks right here are actually the fast bin pointers. So right here, this is the size of 30, and we see that our fast bin is a size 30, and there's a 1 there specifying that the size of 30 is in use. That doesn't sound quite right, but I'm going to go with it. After the fast bins comes down to this guy, this is actually going to be the pointer to the wilderness, or the top chunk. So if you're to allocate a brand new piece of memory that's within the current size frame, it would actually be put at this location. This value right here, that's 0 right now, that would be the location inside an unsorted bin if you were to allocate something. Right now this is just an unsorted bin, and it's saying that we haven't allocated anything from it. That's why this is 0. So if you were to allocate, if you were to allocate a new chunk that's smaller than 0x_0, instead of taking from the top wilderness, it would take from the unsorted bin first. Then we just have the big list of small bins, which range from, I think it's from 20 outside of the fast bin up to 0x400, and then the large bin list that goes up from that. But this pretty much is just a doubly linked list at this point, where it just continues from the same size, pointing to the next chunk and over and over. So here's the kind of what the metadata will look like. So when you allocate a chunk, this is what you're given. You'll be given like the address at this point, and this is where you can actually put your data. But what will be changed is the first 8 bytes before, where it'll put your size, and then it will mess with the last 3 bits also. And what this is for these 3 bits, I guess. The allocated arena, whether it's mmapped, and then the previous in use. So usually you'll just see the previous in use, so it'll just be the size and then 1. So if we go back, we don't really have an example right now, but I'll be sure to show it later. And then if you free that chunk, and it's in the, kind of depending on where it's at, this is more of a small bin, I guess, where the size will be the same, the previous in use will be the same, but it'll now add these forward and backward pointers. If it's a large chunk, it'll have the next size and the back size, because The large chunks kind of act differently than anything else, but you don't really. In a lot of exploits, you kind of might not deal with them, so you're not going to worry about too much. And then the last 8 bytes will also be set to the previous size to tell. So when it's actually walking through and might be working for consolidation of similar sized chunks or similar free chunks, it actually do some checks to make sure the previous size actually lines up with different chunks, and this can lead to more exploits as long as some of the pointers line up. But all you really need to know is that there's going to be a forward pointer at the first 8 bytes inside the actual memory chunk you can write to, and there's going to be the next 8 bytes will be the backward chunk, and then we'll talk about this later, but in small bins and unsorted bins, there's kind of some checks to make sure that the forwards pointer, backward pointer actually points to this chunk. And that's kind of just making sure that the doubly linked list is actually correct, and if it's not, there's a good chance that it's been messed with, or if it's been overwritten, and that can cause problems or exploits that we'll talk about in the future. So here's a little bit about fast bins. Fast bins are like Tcache bin, or like the Tcache, where I guess Tcache is kind of like fast bins as Tcache came after. But fast bins have a little bit more restrictions as they've been around longer. There's no length restrictions as in Tcache, like as in when you do Tcache and you're free 7 items, they're not going to add to the Tcache list anymore. Whereas fast bins, as long as you keep freeing the same size without consolidating them, it's just going to keep adding to the list, and it can be infinitely long. They're usually defined as sizes 0x20 between 0x80, and we saw that with this slide. You can see right there. But you can actually change that during mid-exploit, and I might talk about that a little bit today. Probably kind of stay away from that because that's not really that important of knowledge. And there's no complex check for double freeze. So in recent libcs for Tcache, if you were to free something for Tcache size and then free it again, it'll recognize it's a double free no matter what, as long as it's already in that list. Whereas fast bins, if you were to free one fast bin, free another, and then free the first one again, it'll just put back into that list, and then you just have a easy kind of fast bin dupe, or are able to get a fast bin pointer to somewhere else. So here's a little bit extra. As I said earlier, the allocs are used for the heap, calloc overall. So calloc is kind of a function where you allocate something, it'll zero it out for you. It doesn't actually use Tcache. It'll just go straight from the fast bins or unsorted bin or small bins. It's actually possible to avoid zeroing out a chunk in calloc, whereas if the M-mapped bit is set, this is kind of making the calloc think that, hey, we just M-mapped this chunk. There's no way someone already wrote anything to it. It's already going to be 0. We can just calloc it, give them the address or the space, and we don't need to worry about setting it to 0. There's also hooks for many of these alloc functions. So there's a malloc hook, a realloc hook, a memoline hook, and then a free hook. So what the hooks overall do is that if you're able to overwrite the hooks and then you call those functions, whatever's at that address in the hook will be called. So what a common thing to do is overwrite a free hook with system, and then now whenever you free a chunk, you'll just be calling system on that chunk overall too. So that's what we'll be doing later today. Malloc consolidate joins together chunks, and this only gets called in certain circumstances. So if you were to free a bunch of fast bins, they'll probably be put on the fast bin list, but they won't actually be consolidated, and we'll see that later. But if you were to free a chunk larger than a fast bin, then it usually call malloc consolidate, and it'll kind of try and bring all the space together to give the user more access to larger chunks. And then if you were to just kind of allocate a huge chunk overall, it'll also call malloc consolidate to see if it could maybe get another chunk in there. But yeah, you just need to know that malloc consolidate is important, as it will cause a lot of problems if your fast bins don't line up correctly, or if you overwrote some pointers and caused ability for some kind of errors to show up, because there's a lot of checks to make sure all the pointers and doubly linked lists are correct when you call malloc consolidate. So that's all I had for slides, and I'm going to go into a challenge walkthrough. And this week we're going to go over the childish calloc challenge from the Hack the Box CTF qualifications that just came out, or that we just did a couple weeks ago. not really, can't remember the day we actually did. I think the 20th of November. But during the challenge, the description is kind of leading you to say there's a way to do a House of Force exploit, but during the actual competition, I wasn't able to find it and found a different, completely obscure way, I thought, to actually get the challenge done. But here I'll actually go over that House of Force example and kind of show you what was meant to be done with the challenge. So we don't actually have any source code, so we'll have to start reversing by hand again. And we can kind of see, probably, yeah, we'll just go here. So we can kind of see what's actually happening. So this string's getting printed. It doesn't really matter too much. We just see that we get a scanf on %d, and then it's compared to this jump table. So we have four functions overall, but we'll do a quick run of the binary to see what we're actually working with. We can see that we can find a toy, fix a toy, examine a toy, and save a big toy. And then give up, we'll just call exit. So we know we have case 1, 2, 3, so we'll just rename these. Case 1 will be find with an E for some reason. We have fix. We have examine. And we have save. So we'll go through and check to see what's actually happening each one. So first it's going to check to see if our value at this location is equal to 15. So maybe it's just checking to see if we have 15 values allocated. And if we actually check, we can see it's only being written to right here, which is going to be a +1. So we can never actually go down in amount. So once we allocate 15 new chunks, we can kind of say we probably won't have any more. After that, we choose an index. It'll load the index from memory. It'll check to see if it's 0. So that means if an index is already allocated, we can't allocate back into it. It will check to see if it's 0 again. I'm not really sure what's going on there. Or maybe it's just comparing between 0 and 15 now. That could be it. Maybe it checks the memory address and then goes 0 for 15. We're doing a scanf to see how much space we want. It looks like our size has to be between 1F and 3.8 hex. Since it's doing a jump below or equal, it's doing an unsigned jump. So we can't go under or we can't overflow it. And then what's important is that it's calling calc. Since we probably could see the name is childish calc, we can probably assume that has to do with the majority of the challenge is using calc. But after we get that, we come down here and we get the read. But another thing to notice is that right here, the number of bytes, if we were to follow this, we could see it's put an memb, whatever. It's used from the scanf, but what's important is that there's this +1 before it's actually called. So we kind of already see that we have a off by 1 in our kind of overall scheme of reading to the chunks. So if we go over to examine now, we can see that it's checking to see if this value is set to 1, and it sets it to 1 right here, so it looks like we only get one chance to actually check. It lets us choose an index, make sure the index is between 0 and 15, and it exists. And then if it is, it looks like it just prints off the index value to us. Inside fix, chooses an index. Doesn't look like there's any check to make sure if it's between 15 or if there's one try, I guess. So we have multiple tries at this. Make sure it's actually allocated, 0, 15. Looks like it frees it. Asks us how much space we need for a new one, scans Fs, does the same size comparison, calcs is a new chunk, does a read, but we don't see a +1 this time. And then it looks like there's another question like, do you want to verify if it's 1 or 2? It'll either print out the data we just put in or just exit, and then we should only have one try at that too. But another thing you should notice is that right here is that since we're working in the same index this whole time, if we free a chunk and fail this check, we're actually going to jump straight to the end, and we kind of have a use after free just sitting right there now. And it's not really going to cause any, or it's going to cause problems for them, I guess, because that's going to be our exploit or our exploit point of contact, I guess, whatever. So here inside save, we'll check to see if this number is set to 1, or if this number, or I guess see if it's 0, if this is 0. Then we check to see how much space we want, and we do a comparison to 5AF and then F5C0, and then we'll malloc a chunk if it's between those two, but we'll also set the first one to the size and then the second one to the value returned by malloc. Now, what I missed during the actual competition was this check, or these checks, is that they're compared to AX and not RAX. And what this is important is because we can set AX to be within this range quite easily, but if we set RAX to an obscenely large number, we're actually able to possibly get allocation kind of wherever we want, and we'll show that with the House of Force technique. So that's all we have for the main functions. I'll go into this init function right here, which is called before our main actually runs, and you can see that it sets the alarm, some buffer handling, but it's also going to do these mallocs and more mallocs. And what's actually happening is it's mallocing 20 hex and 30 hex 7 times each and then freeing them all. And what this does is it's actually going to fill up the T cache for us, so we don't have to worry about it. So if we just start and then do heap bins. Oh, it didn't actually break at main. Break at main. Alright, run. Heap bins, we can see that they're both already full with the count of 7. Okay, so we kind of got through everything here, so now we can... So our kind of main goal is to get a House of Force going and kind of get an overall understanding of what the heap looks like. So what a House of Force kind of is in general is that if we go to our heap bins, we can go check out just any random chunk, because all we want is the final one. Is this right here is going to be the top chunk, so everything below it is unallocated, is what we're saying, and we could go through the arena to see that it's going to point right here too. But if we can make this an obscenely large number, that's going to make malloc think that now we control all the memory after this address also. So if we were to actually get this to a size, let's say large enough to, I don't know, if we were just put all F's in there, I guess, we could then allocate a chunk to make us line up to somewhere inside libc, because the heap is before libc, and then after that we could allocate a small chunk, because that's what we can actually only really control, and from there we could probably get arbitrary right wherever we want inside libc, and that's what we're going to target. So I got this template. The exploit's just a test script I did to make sure I could get this working actually, so hopefully we can get that going without having to reference it. So here we have this template. So first would probably be a good idea is to find a way to leak some memory, because right now we have no idea where we are, and possibly get some overlapping chunks, because that's kind of the main goal of any heap exploit, is as long as you can get overlapping chunks, let's say one chunk that can override another chunk size or pointer, then you can kind of, usually most of the time, have complete control of the heap overall. So if we just allocate a chunk, so we have, I'll go through the functions quick. We have send, this is just going to send a string. We have send to, this is just going to send a string, but this time it's not going to send a new line after. This will be important if we're trying to get byte precision and don't want the new line to mess everything up. Find, we'll call the find function with the original send. Find to, we'll just call send to, I guess, kind of this, as you can see. Fix just as the fix. Fix to does the use after free bug, so it'll free the chunk and then just exit out of that function so we don't have to worry about it. Examine will view our piece of memory, and then save will do the save function for us. So what we're going to want is to find 0. What size? We want a size of between 3. Our chunk sizes are between 1F and 3.8 hex. So let's just go 3.8 for now. I'm just going to put an A in there and probably just copy it a couple times. We need to make sure they're all in different indexes, because otherwise the program will kind of freak out because I don't have error handling to check to make sure that I did it correctly, so I just have to keep track of it over in my head. So we can just do this quick to see what it looks like. Oh, not that. Do Python template. If we do heap bins, go over to them, and here we have A. So here's our 3 chunks, and we can see that the top chunk moved down and actually changed values, which will happen in these kind of circumstances. So we can use that use after free to get the libc address, which is what we kind of want first. So if we were to, we can actually use the use after free and the off by 1 at the same time. So what we need to do is, if we just keep freeing chunks inside the fast bin, the list will just keep going and going, but we never actually get a libc value. So what we want to do is actually get an unsorted bin into that list. We can do that by allocating 3 chunks. We'll call this D. Probably change these to C and B. If we free 0, yeah. Actually, let's change this to 14, 13, and 12, because we just want them out of our way. And let's add another one right here. That actually be 14, 13, oops, 12, 11. We'll change this to a 2. So what we're going to do is free 0, and we allocate. That was going to be 1. There we go. That's what I was looking for. Then we'll find 11, 0x38, and this will be, call it A again. Actually, we don't want A. We'll go P64, 0 times 3867 plus the 1 byte, which will be C0. Let me finish this, and I'll walk you through what I'm actually hoping to do here. So here, before I do this one, I'll just show you what the free is not defined. Fix 2. So we'll look at our heap bins, and we can see that after we free 0, it's going to be put in the fast bin. So that means the next allocation, just like Tcache, will be from this size, but since calc ignores Tcache, it's going to go straight into the fast bins. So if we allocate a chunk, it'll give us this one, which is going to be right before our index of 1. So we do this now. Go into it. And we're right here. So here's actually where 0 and 11 both point to. Here's we overwrote this to C0, because now if we were to count it out, it'd be 1, 2, 3. Actually, want that to be C1, because I'll show you why in a little bit. 1, 2, 3. So it's actually now, when we free it, it's actually going to think that it's this huge block instead of just this one small chunk. And since it's not going to be connecting to the top chunk, it's going to put an unsorted bin at this location. And that's kind of the only reason this chunk is here right now, is to make sure that it doesn't consolidate with the top chunk overall. So if we continue and just free 0, not 0, whoops, I wanted 1. That's okay. I think this should still work. 2, 1, 0. Check out our heap bins. Yeah, I think that one screwed it up a little bit. We want C1, and then we can fix up index 1, size 0. Should be an unsorted bins. Oh, nope, not yet. So yeah. So we can see that it actually worked correctly. It's actually put into Tcache first, and we're currently at index of 1. So if we were to do this a couple more times, to make a quick for loop, for x in range of 8, we do fix 2 of 1. And we can see now we have an unsorted bin at this location, as well as the Tcache pointing to it 7 times, but that's not as important. And what's important is that these values are actually going to be placed in here, and these are both pointers to make sure that the doubly linked list of an unsorted bin is actually held true. And you can see that they actually point to the value right before their location. So this is to say that pretend this is kind of a heap chunk. This would be the forward pointer, this would be the back pointer, and it points to the same value, so we can make sure that they kind of point to each other. So from this, we're able to leak this with our examine. So if we do examine 1, I'm going to do an interactive right here to see what it kind of looks like. So it looks like we can split on a space and then 2 new lines. So we can do a p.read until 2 new lines. This will be our leak. Let's get rid of the first character, which is the space, and then the last 2 characters, which are new lines. And then we can do a unpack 64 plus, since it's going to be a libc address, there's a good chance it's going to be 6 bytes overall. So we can just put \00, \00. And if we print the hex of the leak, we should see that it is correct. So that looks pretty right. And it points straight to the spot as last time. Awesome. So now we have a libc leak already. From this, we could figure out the offsets, but we're going to probably worry about that a little later in the future. Right now, all that's important is that we actually have this leak. So next, our kind of overall goal is to get a house of force going where we're able to get a chunk large enough at the free hook. And this is where the free hook's located, so we can actually find this offset. Let's do and this is going to be after the arena pretty much every time. We can see that it's the arena plus this large value. So we can add that quick. So free underscore hook is equal to leak plus this. And we might as well find system while we're here also. So system's going to be in the text section, which is going to definitely be before the arena. So do this minus system. So we can take this there. Oops. System is equal to leak minus that. Okay, so now we have free hook and system. So to actually get this to work, as I said earlier, we'll need to be able to overwrite the top chunk size to make this be something large enough where we are able to free a chunk large enough. So mmap isn't called and we're able to get into the free hook area. So the only way we can actually do that is if we're able to get some kind of consolidation going where we have overlap necessary to allow us to get this kind of exploit going. So the problem with this is that if we I'll kind of show you how the consolidation works. So if we do FG there, an easy way just getting consolidation going is since we're using scanf, we can actually just get scanf uses the heap and malloc to handle any buffer that's larger than it's kind of expecting or kind of just obscenely large stuff. So if it's over like 512 characters, it'll be put into the heap. So if you just put in a bunch of zeros because they're using %d, and if you put in a character, it would kind of break the standard input. We can see that it actually didn't do what I wanted because I didn't free that chunk first. Let's try that one more time. Fix 14 and then do that one more time. So now I freed the bottom chunk, so that'd be in the fast bins. So we have the unsorted bin and then the chunk that comes right after it, which we were using as kind of a handler between the top chunk, the wilderness, and the current chunk we were faking. But if we were to do this, we can see now that the unsorted bin is gone and there's nothing, and our fast bin is gone too. That's because the chunk consolidated. And if we go here, we can see that there's a bunch of ones here, or zeros here now. And if we go -16, we can see that its size changed to the top of the wilderness. And if we were to check the pointer for the wilderness, it would point to right here also. So that kind of causes some problems for us. But if we're able to get a chunk that possibly points right here, we could overwrite that quite easily. So that's our goal. And this is kind of the hardest part of all heap challenges, is just trying to get chunks lined up correctly and make sure that everything works nicely without it crashing. And that's where a lot of this challenge is going to lie. I'm going to open this to make sure I have it the correct solution off screen, because I don't want to waste an hour of your guys' time, because I got lost a couple times trying to get this to work correctly. So what we're going to do is we have a way to leak it, and now we want a way to kind of get an overlap going. I'm going to kind of just ignore this top part for now and kind of show you our method for getting an overlap, and then I'll rearrange it to be in the correct order we need for the exploit to actually work. So right now, 1 points to a fake chunk of size 0xc0, but in all occurrences it is pretty much a real a chunk of that size. And if we were to allocate a new chunk of 0x38, it'll probably take from that chunk and give us something just like it. But if we were to fix 2,0 again and change the size one more time, because if we were to free this, if we were to free chunk 1 again, it would see that it's already in the unsorted bin list and throw an error saying double free. But if we change this back to a 4.1 it was at earlier, come on, whoops, now we're able to free 1, and we should be able to see that it's both in the, oops, fix 2, and it didn't do what I wanted. What? Oh, 11's already used. 10. Heap bins. We can see that we both have the fast bin, a fast bin pointing to the chunk, and the small bin pointing to the chunk at the same time. So from here, we could probably just do a fix on index 13, 0, and we can fix 1 again. And now we'll see in our fast bin list we have this loop going on. So 1 points to 13, points back to 1. And this is important for us because now if we're able to overwrite 1, when we allocate 13, it'll go back to 1, which will point to somewhere else. So we kind of actually fake out this list to make us get a chunk wherever we want. So if we just change this to, if we change this pointer, which is right now pointing to the B, but once we allocate a new chunk, it'll, since B points here, the list makes it think that it's still possible. So if we were to overwrite this with just a 1 byte value to get to this address, we wouldn't need to know where we're at, and we could trying to think of how I did this. If we can overwrite this with a 1 byte value, we can make it think that it's or we can get a fake chunk right here, and we can get the overwrite we need when we consolidate the chunk back to the top. So to do this, we are going to use that nifty little trick of making it think it's an mmap chunk. Oops. So we'll change this to a 3 by setting the second bit. So we'll fix 2.1, fix 2.13, fix 2.1. Now if we allocate find 0x, oops, we'll go over to 9, 3.8, just put an, oh, we don't want to put an A, I'm going to find, so this will be put into index 1's location, and we're going to just put a, I think a 90 is where we want it to be. And if we find another one, this will be in location 13's index, \90, then this one should be in that one, I think. Let me see what I did wrong. Fix 2.13. Why did that crash? It worked when we did it last time. Invalid pointer. Oh, that's because I did this. Oh yeah. So here's kind of another issue we're running into, is that we can't free an mmap chunk because it's going to freak out at you and say, this chunk isn't nmapped, it's not at the top of the heap, it's going to then cause problems. So we'll do this, get that, we'll check to see what our heap bins looks like, and right now we have a pointer to the 1 and then a pointer to 0, because that's what was put in there after the, actually it's 90, but then the calc has zeroed it all out, so at that point we kind of lost because that's definitely not what we wanted. So if I look back, I'm going to start rearranging some stuff to probably to make sure everything works correctly. But it looks like we're going to fix this, then we're going to fix 0, and we'll change the size one more time. Actually, we'll probably do this a couple more times, but change it to 3 now because we can't free it, but we can allocate it. That's what matters. So we'll find a chunk of 90. Yep. Ooh, that's what I did. That's pretty smart. Okay. So instead of finding a chunk of 2, we're actually going to do a fix. Yeah, fix of 14. So what that's going to do is it's going to free 14. It's going to then reallocate a new chunk. But since 14 was 2.8, it's going to put 2.8 onto its free fast bin list, and then take off the 3.8 that we have and put 9.8, 90 in there. Which I think, if I check, I think our fixes are different. Definitely different. I'm going to change this up a little bit. If done is equal to 0, done plus equals 1, send 1, else send 2. So what this is going to do is handle that case where it's going to actually print for us. So this would be a way for us to leak the heap. So if we go over to fix, we can see this part down here, and we can only do it once because it's set with this D word. So many just one-time operations that kind of cause problems, but it is what it is. Done equals 0. Don't need to worry about that. Then I'm going to change this to a send 2 because it doesn't hurt us overall because we're only really calling this in certain circumstances, but it'll help with our 0x90 overwrite. So we'll set that for now, and we'll check to see what we're working with. I think I might have missed something. Fix 14 with 0x38 and 0x90. Why did that cause problems? Oh, 10. Let's change that to a 9. Check out our heap bins. We can see that 30, which is going to be the 2.8 size, is there. It's now on. And then we actually have this previous and is mapped. So if you actually check out this chunk, we can see that we successfully wrote that 90 there, as well as I was really hoping it would leak it back to us, and it should, unless I mess something up. Choose an index. I think I might have send 2. What is that not printing out the leak for? If done is equal to 0, done plus equals 1, send 1, else, oh, that's why. There it is. So now we have a heap leak also, which we needed for the exact value that I'll talk about in a little bit. So we can kind of just do the same kind of leak pull here. I'm going to save this as C is equal to leak, just in case we need it in the future. That should be the exact same, and then heap is equal to leak. And print the hex of leak. So we can see that we have this address, and that should be the right value for... It is not, and I know why. Right now it's pointing to 69, but what we wanted to have it point to was 59, and I was off by... I was off because I was using 13, whereas 13 just barely crosses the border into the next chunk, so let's actually switch that 13 with 12. And now we should have a 590, and if we check to see that chunk location, it actually points to be right here. And if we check our heap bins, we can see that we have the 5A0, which is going to be 10 off of what it thought it was, because that's kind of just how the heap works. It'll check the... We want this pointer will point to the pretty much 16 bytes before the address it'll give you, but it'll actually be at this address and below. Whoops, this address and below. So all we need to do is allocate 2 chunks for 0x38, and then the third chunk will be at this location. So let's do that quick. Do a find on 8, 0x38. Just put an A in there, probably copy it, put 7. Kind of being a little loose with our allocations, but at this point we kind of have to realize that we're running extremely low, as we only have 2, 3, 4, 5, 6 left. But we're not going to care about that too much. I'm going to save this one just to show you our heap bins again. So we can see our value that we wanted to overwrite is now at the top. And if we were to allocate the next one, find, put it into index 6, 38, that's 48, 56. We can see that we actually have a corruption on the fast. So if we actually check out our bins, what's happening is that one of the... Oh, it actually cleared it. One of the checks that fast bins does that Tcache doesn't is that it makes sure that minus 16, because this will be the chunk we're at. It wants to make sure, or it has to make sure that the previous size, or not the previous size, that its projected size pointer is actually correct. So we'll have to make this value right here be 41, and then we'll also need a fake pointer down here to actually make it think that there's another chunk at the bottom. So we can do that by spamming 1s in here. That doesn't seem right, so I'm not going to do that one. Right here we'll spam some 4-1s though. Oops, 0x41. Actually, that's also not right, because that'll be zeroed out with this one and this one. So we'll put a 0x41 in this one. Now, when we allocate our first one, which should be this one, this will overwrite the... It won't overwrite because I forgot we're using 4-3. So we do want to put the 4-1s in here. So usually you kind of want to be precise with these, but I just kind of am going to spam them in just to say that it works. And if we want to check to make sure everything actually looks right, we can go in here. So here, if we go 16, we can see that we now have a fake size. And we go 1, 2, 3, 4, we have a fake size right here. What I don't like about the spamming everywhere is this, is now we have the corrupted fast bin. And when we try to consolidate, because we want to get the top wilderness right here, that's actually going to cause problems in the fact that it's going to say, hey, your chunk right here is actually... it's going to try and figure out where this is pointing to, and then it's just going to segfault because 0x51 is not a real address. So let's change this from 7 to 6. Not that one. This one from 7 to 6 plus P64. Whoops. 6 plus P64 0. And now we can see that it's the correct, or it's going to seem to be the correct size. And if we allocate another chunk, think 5? I think 6 was also right, but it doesn't matter too much. 56, and we'll just put A, B, C, D, E, F, G in there. We can check out the chunk, and we can see that we now have the string A, B, C, D You're probably thinking, well, this kind of looks wrong, but that's because this chunk isn't 4-3, so it's going to overwrite everything, which I think might cause some problems with, yeah, it'll definitely cause problems with this, because the unsorted bin, when it consolidates correctly, it wants to make sure that this is all right, but it is definitely not all right at the moment. So we need to find a way to, one, get all of this lined up correctly so everything works in the correct order, and two, to make sure that everything still functions in the normal heap context. Quote unquote normal, because this isn't really what the heap was designed to be exploited for, but so I'm going to have to start moving some stuff around. So I'm going to set, at the current path, when I was doing this for this meeting, I was going down this, I'd leaked libc, I had gotten to this point, and I was thinking, well, I definitely don't have enough chunks to do what I want, because we have 6, 5, 4, 3, and 2. That's only 5 chunks. It takes a chunk pretty much every time we want to rewrite the size of 0 or the index 1, but 0, and we need to do that again. So I needed to find a way to actually get this lined up correctly, and this actually is possible if we move the first leak up here. Whoops, let's just get that. We can get this is there. We're going to want to move this guy up here. Change this from 9 to 11 because now the order is all different. We'll fix with the 90. Then we can leak the heap. Then from the heap leak, we can allocate what is, oh yeah, I know what I was doing. We're going to allocate these 2 chunks because we want to get the pointer up there first before we try and consolidate. Because another reason for that is if the other method I was trying to consolidate was trying to use scanf, and as you saw, scanf will toss all of those bytes in there that we actually sent in. So in this case, it'd be like 0x30 or 0x31 if it's the number 1 a bunch of times. And that also causes problems because those aren't valid sizes for a pointer to point to, and this caused a lot of headaches trying to line this all up. So if we line it up beforehand and then just consolidate all at once, we're able to get a clean leak that way. So we'll get those 2. The next we're going to put into 3. I think I just skipped 2 though. Find 0x38. We'll put P64 of 0 plus P64 of 0xC1. So what this is doing is this will be our overlap chunk, and what we kind of did is just saved us interaction right here. By getting the overlap, we're able to overwrite the size to get our libc leak that we want, as well as clean up the T-cache at the same time. So now we're able to do this free, and everything from there is about the same until get rid of this one. So let's take a look to see what we're working with. So right now we have one size 28, which was 14, and this guy right here. So I'm kind of surprised that, not really surprised because I knew it wouldn't, but there's a little bit in me that thought, since we had this guy in the fast bin already, no we didn't because we just put him in there, that's why. Yeah, no we didn't, he was definitely already in there. He's been in there for a while. So I was a little surprised that this freed address wasn't consolidated, but apparently malloc consolidate isn't called on unsorted bins all the time. We actually probably just need a larger chunk. Since this guy was free, I'm surprised if it was consolidated, it would have tossed our wilderness pointer all the way up here, but that's not important, I guess. So, get rid of this guy. So now, after cleaning everything up, I think we saved ourselves 1 or 2 interactions. I'm going to change this back to 10 and 11. Not 11, 9. So now we have, switch this one to 2. We have 3, 4, 5, 6, 7, and 8, which I think is, it's only one more, but we're in a better position now because we have a better better locations, and the fast bin isn't all kind of filled with a bunch of garbage values as it kind of was earlier. So now we need to, one, we want to empty out the fast bins because we want not the fast bins, but what we're going to do is we're going to empty out this unsorted bin by allocating a bunch more chunks of 0x38 to fill in these values, and then we're going to free, why did I do that? So I'm just looking at the exploit I did, and it had did an unneeded part. I was just trying to confused on why. But anyways, 7, we go 8, 0x38, P64 of 0x41. We're going to do this times 6. So this will be in location 1 still, because this will be straight from the unsorted bin, and we want this the 0x41 to still be there for if we resize our index 2 when we overwrite the wilderness top chunk pointer or size. So we can also find 7 0x38. We can toss A in there. Now for some reason I find 2 right here, and I know why. I don't actually know why, because that's not needed. Oh wait, 6 0x38. We'll toss with some B. So this will, all 3 of these together will take up the whole small bin or unsorted bin. If we check in there, we can see that the unsorted bin is now gone, and all that's left is this fast bin, which I think we kind of want that gone too, and I think I missed it, but maybe not. So if we now fix 2, our location that's overlapping, we're able to get a larger size than what was available with, which doesn't really matter right now since we're using 2.8. But if we had 3/8 across the board right here, the chunk size would be 0x100, and we're actually since we only have the 1 byte overflow, using the method with index 0 and the overwrite, we're only able to overwrite 1 byte, so we're not able to actually get a chunk to fake a size of 0x100, but this way we are. But since we are only doing that, we only need a size of 0xf0. So this will be a size of 0x38, and we'll put in P64 0 plus P64 of, that might be why I did this. No, maybe not. Okay. P64 0 plus P64 of 0x F0. There was that. Now if we were to check out the current kind of layout of our heap, go to this one. Do -16, we can see that the index 1 is going to have a size of 0x F0, And if we do plus 0x F0, we can see that it points to the end of our allocation. So if we free this, instead of it being an unsorted bin, it should just be consolidated with the top chunk and the value should be moved up. But if we also, I think if we just free it now though, it'll cause problems with this fast bin because there's some overlap and it'll get angry at us. But I kind of want to try it just to see what'll happen. It didn't. Maybe it just doesn't care. No, it definitely didn't do what I thought it was going to, because it didn't consolidate it. Did I do the wrong one? No. Interesting. So I guess it just didn't do anything that time. Oh, yeah, it did. Put it into T cache. Gosh, missed it every time. So let's actually test that out. Let's just do a... I'm just going to copy this again. Never forget about Tcache. It'll always sneak up on you. So as you saw, the program crashed, but we kind of just want to see what the error actually throws at us. Index C. And it looks like corrupted size versus previous size, and this probably has to do mostly with the... I would guess with the fast bin chunk. So if we look at it, minus 16, maybe not. Oh, maybe it's that. That's not nice. I don't think we want that to end with a... That should be end with a 0, I'm pretty sure. I'm not remembering when we overwrote that, if that would have happened. I don't... Maybe I'm thinking of something else. So I'll do a find to... Just do a find, I guess. 5, 0x28 to clean up the fast bin, because I'm pretty sure that's what was breaking it. So before we do the final free, we can see the fast bin is clean. If we fix now, continue that. Index 1 still corrupted. Why are you corrupted? Corrupted size versus previous size, because that shouldn't... Not that. Let's go with this one. We'll grab index this guy. F0 should line up correctly, but I don't like this. Ends with a 2959. It doesn't. I don't think it should end with a 9. I don't remember why that'd be broken though. 596979. I don't think we ever sent in a character that would overwrite it. Alright, let me take a quick look at all of this to see what looks different, and it would definitely be this one. That needs to be a 1. And that was it. So if we check out our heap bins now, and I'll show you what was wrong with it. So we'll do minus 16, and we can see that we have the chunks now at the top. So what was wrong was that this was an F0, and that's saying that this chunk size is size F, but the chunk above it is a size of, or is not in use since the 0 bit was, or since it was 0, it was not in use. So it was checking right here to see what the size above it, because it thinks that the chunk above it's going to be an unsorted bin or a small bin or something. But since this is 0, it's not going to be able to find it correctly, so it's going to throw an error saying the sizes don't line up. And that's not what we wanted. But now that we have that all good, all we need to do is reallocate this chunk, overwrite this with a large value, and then allocate a huge chunk, and we should be good to go, I think. So now that we actually had that work correctly, I want to check to see if we can do this with the fast bin being broken. Because right now our fast bin is like this. Do a quick free index 0. Okay, so it still didn't like it. No big deal. So we'll change this to 8 to get the leak in there. Can now do a fix not fix 2, fix just straight up 2, 0x38, free it, reallocate the same chunk. Then we want to put a size of just something large enough, so probably 1 like that times 7. Probably want to do, it needs to be end in a, I always thought it had to end with a 0, but since it was a 9 earlier, maybe it doesn't, and I was just messing up something earlier in my tests, but I'm just going to do this to make sure that it seems appropriately safe. So if we want to check to see what it looks like, we do a minus 16, we can see that I'm off by 8 bytes. P64 0. Just take this one actually. Oh, not that one. This one. Not that one. This one. And we can see that the size is actually overwritten now. And if we just like prove that's true, we can check to see the actual address pointer, which would be this one. And you can see that this value changed. This was when we allocated the values within the unsorted bin, so this just was pointing to it, but since this value points to itself now, it realizes there's no use to really look at it. So yeah, so the top chunk points to this address, so if we were to allocate something really large, we should be able to now. So what we want to do is figure out where we're kind of, or what size we're actually allocating. So if we take this, print this minus this guy, we have this large value. And if we look at the bottom, not nibble, word, and compare it to inside, say for big toy, we can see that this word is actually within these bounds. So we don't have to worry too much about it. So we can just allocate a chunk of that size. And we can show that by doing this. Actually, I'm not going to do it by hand because I don't want to deal with actually doing all of that. But save a chunk of free hook minus the heap. And that'll give us a size if we want. I'm going to also subtract 20 because we're off by 20. Then another 10 because that should be the next allocation. And we'll check to see where we're at right there. So the fastest way to just figure out where we're at actually is to do this, check this guy. And we can see that this changed monumentally, where it used to be in the heap with a 5, now we're actually in libc. And we can see that if we plus 8, here's free hook. But what we don't like is this. The value didn't actually update correctly. And what it would look like is that this top of the top chunk value should be a 0xFF whatever and should have modified correctly. And through some testing, I have no idea why, but if I just subtract another 0x20, it should work. And there we go. So now we have this top trunk, and you're probably thinking, whoa, why didn't that work? I got no idea. For some reason, 0x40 would also just leave 0. But 50 it works, 60 it works, 70 it works, I don't know. And it has nothing to do with the value already being in this location, because I also tried overwriting malloc hook and overwrote a value in this and malloc hook's equivalent of this. So I have really no idea if we accidentally hit a magic border between some values, but what does matter is that if we allocate a chunk of 20, 30, we should be able to overwrite it. And that's what we'll do. So I think we should have index 3, 56. We'll just put a bunch of A's in there. I think I just broke it. XCGX address of free hook. Nope. I mean, we did break it, but I think it's because we overwrote something else. I don't know. But we did overwrite free hook, and that's all that really matters. So let's find a toy index 3, 0x38. We'll do P64, 0 times 5. plus P64 of system. Now if we check x16 address of, so yeah, I'm not really sure why it hung last time, but it did. We can see that we have a new value in there. If we print off the address of system, we can see that it's actually the value of system. So if we free a chunk and it contains the string bin sh, we'll have a shell. So I think if we actually just do bin sh, that won't work because I can't send it in null byte or new line. I'll have to probably, I think this one should work. 6 bin sh. Let's free up index 6, and we have a shell. And from there you could get the flag if you wanted it, or live off this adrenaline high that you got from doing an exploit. So that was kind of a lot for your first kind of real heap exploit. I mean, Tcache exploits are real exploits too, but these are kind of more complex and require more correct overlapping and a lot of trial and error until you get the heap in the way you wanted it. And this is kind of where just the majority of heap exploits either win or fail, is being able to get correct overlapping chunks and kind of being able to get the overwrites they need or leaks. But yeah, are there any questions?
That was freaking amazing. I always wondered how you did that challenge.
Oh, this wasn't how I did it though.
I know.
Yeah, so since I didn't see the 1 byte comparison, I think okay. Since I didn't see the 1 byte comparison, or not 1 byte, but 1 word comparison here, I didn't figure out that I was able to allocate a huge size. So I was able to get overlapping chunks pretty much the same way and leak libc the same way. But what I did was used an unsorted bin attack, where if we kind of want to step back, but instead I'm just going to change to the actual one. CTF / box collegiate 2020 qual pwn. Increase the size a little bit. I think if we do right here somewhere, I should be able to jump in right here. I guess I could have, yeah, I could just do it in the actual exits. My exploits go down to where we do our unsorted bin. We'll just do interaction right here, and we'll attach GDB to see what it looks like. Whoops, takes at least P. So we can see that we have this unsorted bin. So what the unsorted bin attack is if we overwrite this address, so we'll set this to go long pointer equal to -1, and check it out. Where now this, if we checked out our heap bins, it would, right now it would still look the same, but it's kind of broken. So the next allocation we have that actually takes from that bin, I'm pretty sure. Go next 5, 3, no, 5, 6, A, B, C, D. Did I? Yeah, it took from it. But I don't think it did what I wanted. -16. Yeah, it definitely didn't do what I wanted it. How did I do that? I guess I shouldn't have closed that terminal. Collegiate pwn. Childish. unsorted bin, leaked it, put the bin on the fast bin list. Break it off. Yeah, the next right here. Attach P. It's weird that it wasn't. I think I'm connected to the Docker right now. Oops. So we can look at it. What I did was overwrote the backward pointer. So right here, I changed this slightly. Usually it'd be like 3661 C0 F0 or 40 or something close to that, but I changed it to something that's way off. And if we actually look, there's just this, in like absolutely no reason, there's just this lone value of 80 sitting here. I lost it. Oh, there it is. It's actually right after free hook, surprisingly. I didn't know that. But if you overwrite this value of 80, this is actually what dictates what sizes are in the fast bins. So I do an unsorted bin attack, which is by overwriting the fast or the backward pointer, you're able to place the address, the next address into that backward pointer. So if we allocate a chunk to size 48, nope, index 5, it's already full, index 6, index 4, index 9, there we go, 48, fast bin corruption, maybe 48 was too large, because I think I have it looking like a smaller chunk, index 8, 38 is too small, I think 40, there we go. Heap bins, so right now the unsorted bin is absolutely broken, but if we go check out the address, I think this is it. Yep. So instead of the 80 being here, it actually placed the forward pointer here. And that's just kind of how unsorted bins, for some reason, it'll place, or not the forward pointer, but the unsorted bin pointer at this location. So now if we made a chunk look like it was size 0x5 million or something, we can actually get a chunk to we can actually overwrite free hook with a chunk, and then from there I just did a lot of garbage stuff, but I was able to make it overwrite values I shouldn't have been able to with unsorted bin, and it was a lot of pain. But yeah.
See, it's just crazy to me that you figured out another way to do it. Like an unintended solution.
It was a lot of pain, but it paid off.
Yeah.
Yeah, Logan.
Thanks.